A full adder is another basic combination logic module that may be available in the market, and we know that addition is the basis of many arithmetic operations, and sometimes multiplication, division, and subtraction may be achieved or implemented with many additive procedures, and therefore an adder is a very important device or module that in digital logic circuit. Therefore, we'll see how can we achieve a gate level implementation of a full adder. The half adder is implemented in a similar manner, therefore we will just consider the full adder, and it's more or less the half adders can be achieved in a much easier way than the full adder. So we notice that a full adder takes into consideration the possibility of an input carry bit, whereas the half adder does not. Again, for instance, we have talking about adding binary numbers A and B, A plus B. We normally say that the answer would be 1, 0. For instance, if this one was 1 and this one was 1. But assume we wanted to add such a number as AB plus BC, which we can say that AB was 1, 1 and BC is 0, 1. What happens? What we know is that with half adder, you'd be able to say this is 1 plus 1 is 1, 0, but you cannot carry this one so that you can add it to this other higher order or more significant bit. So with half adder, you only do 1 plus 1 is 0. You discard that carry bit, then you say 1 plus 0, you say this is 1. So this would give a wrong answer. But with the full adder, it allows a carry bit, and therefore we say we will carry this 1, you add it to that, becomes 0 again, like that. And if you look at the numerical representation of these digits, this would be a 3 and this would be a 1, which the answer becomes 4. But with half adder, you only got 1, 0, which was a 2, which is an incorrect addition. But with full adder, you get the correct solution, which is 1, 0, 0. So having demonstrated the functionalities of a full adder, then we say that let's consider a full adder with added bit being an and an OR bit being bn and a carry bit cn minus 1. So the same way I have said, we are talking about adding a plus b, but we are considering we may have carried some carry bit and cn minus 1, where this is a n and bn. We are simply saying adding them in the form that we have been saying, where we are saying, assume we are adding a plus b, like 1 plus 1, but with the possibility of a carry bit that is coming from the previous operation, cn minus 1. That is why we are talking about n minus 1, because we always carry from a previous operation. So like we did 1 plus 1, adding them down, this is our a, this is our b, and therefore if we have a carry, we say that 1 plus 1 is a 0, carry 1. Therefore, our cn minus 1 would come here as 1. So in few words, that is what our meaning when we talk about augmented and added and a carry. Therefore, the result of such an addition would be sum Sn and an output carry Cn. So again, we are arranging it in this form where we are saying that we have input A, N, another input or augment Bn, we have Cn minus 1, we have our sum Sn and a carry Cn. So we are asking ourselves, if we have A is 1 and Bn is 1 and we have not carried any bit because it's our first summation, this would be our sum is the result of this plus this. This is going to be a 0, but we carry a 1. So I'm already arranging it in a column form so that we know what each of the variables will hold. Again, you can have, assume now we have a carry that we have carried here. This Cn will now become our Cn minus 1 here, and therefore assume we have another 1, 0. You want to add, what we'll say is that this is going to be this plus this becomes our sum, which is 0, carry 1, and our carry 1 becomes right here. So this would allow us to develop some table or some truth table for the possibilities of having A, B, C, Cn minus 1, and for our outputs Csn and Cn, and we'll see that table shortly. The subscripts denote the possession of the significance bit. So our truth table will take this form, that the possible combinations of A, B, and C, they will have all the 8 possible combinations like we have seen before, running from, for instance, value. If you are to give them in terms, this would be 0 and this would be 7. So there are 8 possible combinations of our 3 inputs because we are including a carry. And then we have our sum and we have our carry bit. And simply we have said, if we do this addition of 0 plus 0 plus carry, the sum is what we get after we add 1 plus 1 plus 1. This will become 1, 1, 1. And 1, 1, this is our sum Sn and this is our carry Cn. Only here that they are arranged in a way that you would find them a bit confusing. So having seen this representation of the truth table of a full adder, we can clearly be able to implement gate level implementation of a full adder by simply observing the minterms that are represented by each of the 2 outputs, and we can be able to say that Sn may be represented by a sum or product of 0, 0, 1. Whenever we have the Sn being true, we are saying that is a possible minterm which can be represented in terms of SOP as A bar, B bar, C. For instance, these can have their usual ends, and this is another one. So this becomes A bar, B, C bar, and each one have their own subscripts. So you can do that for all of them, and you can do that similarly for Cn. For instance, the first one is this one, which is true. So this is A bar, B, C, and n minus 1. So another one would be this one, which is 1, 0, 1, meaning A, B bar, C, and each of have their own n's and n minus 1. So you can do that for all of the possible minterms, and we are simply saying that when you fully represent the Sn output, you will find that Sn may be expressed as, so this is the expression for the sum Sn, and this is the sum of product for Cn. And if you solve this further using the usual method of representations of Boolean algebra, you will realize that Sn may be simplified to take the form An XOR Bn XOR Cn minus 1. And what you do with that is simply observe. If you consider the first 2 variables, like here, you'd say that A, if I drop the n's or the subscripts, you can say that if you factor out A, you'll have B bar C or B C bar, and this is the equivalent, which we say this is equivalent to A bar and B XOR C, because we say that exclusive OR means that these 2 terms are always opposite to one another. When one is bar, the other one is not, and when this is not bar, the other one is bar. So we can observe that this becomes our XOR, and if you factor this out, you will again realize that if you factor An, okay, drop the n's, you'll have BC will take this form, which is A into B X nor C, which we can consider to be bad. Remember, this is the opposite of XOR, because XOR will be in this form, but here we are taking when they are the same, and therefore this is the same as X nor. So I'm saying that this is going to be bar. Therefore, when we look at these 2, if you just let this one be, consider this term in bracket to be D, then this other term in the bracket will be D bar. And for that reason, you'll have A bar D or A D bar. And again, you can observe that this is in XOR form, which you can now express it as A XOR D. And for that reason, we are able to finally say, if you replace now this D as this term, you will see that your final expression for Sn becomes A XOR D, which is B XOR C. So this becomes the expression for the sum. That is what I am saying here, that sum will take this form, and our carry Cn will be, if you follow the similar simplification method, you will realize that carry can be expressed as An XOR Bn into bracket Cn minus 1 or An Bn. And therefore, since we have been able now to express our two outputs in terms of this gate level or Boolean level implementation, then you can be able to implement these two circuits at the gate level and be able to demonstrate that an AND can be fully achieved using basic gates. And these gates are simply represented by this diagram right here, because we have seen that our sum can be achieved using two XOR operation consisting of A, B, and C. That is what we have just seen. This is our A XOR B, and this one is what we termed as D, and we are saying this is D XOR C, and therefore this becomes the implementation of the full adder. And for the sake of completeness, this section is equivalent to a half adder that does not consider the carry bit. This is another half adder that does not consist of a carry bit, and therefore this ORing of Cn is the one that now allows us to achieve our full addition, and therefore we have our Sn and our Cn. So the symbol for representing as the full adder is as seen. It has two inputs, A, B. Actually, it has three inputs, A, B, but one is a carry with that one, and the outputs are Cn and Sn.